Hi, in this Let's Create episode, we're going to be creating a Crossy Road clone like this. We've got the character moving in a restrained isometric 3D view using a hopping light animation. The levels are procedurally generated with two terrain types, grass with trees on or roads with cars on. The level gets harder as we progress by putting in more roads and making the cars faster, and we track the furthest the player gets in the UI with a counter, and when you inevitably hit a car, we explode into a bunch of cubes. Let's get started. For this project, I'm using the Universal 3D template in Unity 6.2. We're going to need some graphics for this game. I'm using some public domain models from kenney.nl, an asset creator that releases models into the public domain. Do check them out and consider donating to them if you can use any of their assets. They really are great for prototyping like this. I'm going to use assets from two sets. The first is the holiday kit. I'm going to use this for the cute little reindeer who's going to be our main character. I'm not following the completely blocky style of Crossy Road. You can of course use any models you like in your clone. The second is the car kit. I'm unsurprisingly going to use this for the various cars we'll have on the roads. It's got lots of different models like the police car, this truck and a van. There are loads in here. I'm just going to add a few, but you can add as many as you like to the game when the time comes. Okay. The first thing I'm going to do is right-click Create Folder to create a new directory which I'll call Models. Into this directory, we'll add a few of the models we're going to use. We're going to create two subdirectories, one for the characters and another for the vehicles. Apart from the separation, the reason for this is if you need to import the Textures folder, and from the Kenney assets they have subtly different colour maps. First up, the reindeer with its textures. You can see in the inspector that it's got the reindeer and the correct colours. Almost forgot, we'll need the tree as well to be an obstacle. Then into the other directory, I've chosen 4 of the vehicles: police car, delivery truck, van and sports sedan, again with the textures folder. You can see them all in the inspector nicely there. The first thing we're going to do is get the starting area and the character movement set up. Let's start with the grassy area. This is going to consist of several objects. So we'll right click, create empty to get an empty game object. We'll add all our grass bits into. We'll call this grass. Make sure it's centered at the origin. Right click, 3D object, cube. As I had the grass selected, it already put it as a child. If yours isn't, just drag it under the grass object. Reset the transform if it's not centered already. I want the playable area to be 11 units wide, an odd number so you can start right in the center of it. This is going to be a grid coordinate system based game. We'll want to be moving around at integer positions. More on that later. So let's set the X scale to 11. We want to add a bit of interest to our game. The roads will be lower than the grass, so we'll make the grass 0.2 units high. So that's our Y scale parameter. Z we'll leave at 1. The cube position is from the center. So the top is at 0.1 and the bottom at minus 0.1. We'll just move it up in the Y to 0.1, so the top is at 0.2 where we expect it. Let's make this green. In our assets, create a new folder called Materials. Right click, create material. We'll call this grass. Naturally we'll want it to be green, so choose your favourite lightish green. I'm a stickler for round numbers, so I'll just tidy these up. Let's drag this onto our grass cube to apply it. In Crossy Road, the areas you can't move into are represented with a darker colour. So whilst we're here, we'll duplicate the grass material with Ctrl D, call it Grass OOB for out of bounds, and just make it a little bit darker. Great. Now we'll duplicate our grass and offset it so it sits to one side. We can set the X position to 11 so it perfectly abuts it. We can then add on the darker grass material to it. Then duplicate that and put it on the other side. Okay, so now we've got 1 unit of grass. We want to add some trees to the impassable areas so they act as an obstacle. Drag the tree into the grass game object and position it in the outside area. We can press Shift F to center on the object. Let's set the positions exactly so it's sitting on our grid. Z equals 0, Y equals 0.2 and X equals 6. It's a little big, they'll overlap if placed next to each other. So we'll scale these down to 0.75. You can use the link icon so all the dimensions scale together. That looks good. All that is left is to duplicate the tree a few times and put them in the rest of the positions. I've gone with 3 deep on each side. That's looking good. Let's create a new folder called Prefabs. And to this we'll drag in our grass game object. Let's delete it from our scene for now and we'll create the whole starting area. Right click, create empty game object. We'll call this starting area. Ensure the transform is 0 and reset it if necessary. To this we'll add our grass prefab. We're going to build our procedurally generated levels from z equals 0 onwards. So the starting area we'll put before that. For the first one, we'll set the transform to z equals -1. Then we can duplicate it with Ctrl D and add 3 more at z equals -2, -3 and -4. That's probably big enough. We'll duplicate it one last time at z equals -5. This one's going to be our boundary at the back, so we want to fill it up with trees. So to this one, we'll extend the trees to cover the whole area. I've duplicated the tree 11 times and I'll just go through updating the X position of each of them. With that laborious task out of the way, we can duplicate this a few times and put a little forest at the back. There, I think that's looking good now. That's our starting area complete now. Let's get our little reindeer hopping around our starting area. First up, we need to add them into the scene. Right click, create empty game object, and we'll call this character. We'll move this to the starting position, which will be x equals 0, y equals 0.2, so it sits on the grass, and z equals -1. Under this game object, we'll drag on the character model. You want the model under the game object because you want to use the parent one to control the character moving around the scene, but the child one may have the rotations or animations applied to it. It also lets you easily swap out the character models. We use F again to focus on the reindeer. Like with the tree, the reindeer is a bit big, so we'll scale them down to 0.8 of the original size. Also, I think they're not quite sitting centrally in the square, so we'll adjust the Z to 0.2 to get them looking a little bit better. We're going to need to detect collisions between character and the cars, so we need to add a box collider. We're adding this to the parent object here. Later we'll get our reindeer jumping in an arc, and we don't want the rotation applied to the collider, else you may find it sticks out of the square you're in, which would mean you would collide with things when not expecting them to. I'm just going to adjust the centre and size of the box collider so it's sitting nicely within the reindeer. Once the game is done, you may want to play around with this. Having a larger collider means cars can clip you slightly, causing you to die, which is technically correct, but you'll find that in the gameplay you think you should have missed. So generally it's good to have a slightly smaller colliders and give the player a little grace. Then as we want to detect collisions, we also need the rigid body on the character. We don't want any physics interactions going on though, so we can remove the use gravity setting. In the constraints we can also freeze the positions and rotations so they aren't affected. So we've got a collider that doesn't respond to the world, but will detect collisions. We can also set the collision detection to continuous to get accurate collisions. It's a simple game, so we can take the performance hit of this. Okay, all that's left now is to create an empty game object to be our game manager. In our assets directory, we'll create a new scripts directory. Then right-click, create mono-behavior script, which we'll also call Game Manager. We can drag this onto our Game Manager object and let's dive into some code. In our Game Manager script, we'll get all the variable state set up first. In our using statements, we've got system.collections for coroutines, which we'll use to animate the move, then Unity Engine for all the Unity stuff, and finally Unity Engine.input system for getting the player input. We'll be using the new input system here, more on that later. In our script we only need one object reference right now, that of the character we want to move. This is a serialized field, so we can set it in the inspector, The type is transform because that's the attribute we'll be changing, and it'll obviously be called character. I'm a big fan of headers to variables so that it can be easily separated in the inspector hierarchy. The only variable we need is a game parameter, which is a private float called move duration, which I've set to 0.2. This will be how long it takes our character to move from one space to the next. Next up, we've got a game state. It's always useful maintaining a state machine within your projects so you know where you are. In this case, we've got 3 states: ready, moving, and dead. For example, if you're ready, then you're able to move. You can't move if you're already moving or dead. So we create ourselves a private game state called GameState to store the state of our game. The final variable is a private vector2 int called CharacterPos. As this is essentially a grid movement based game, that is, we're moving between integer coordinates 0, 1, 2, 3, 4, we'll store the position of the character here. We'll not be using its actual position in the world for any logic. Now when we start, we want to make sure everything is where we want it to be. Rather than using the start method, I've put this into awake. It just gets called a tiny bit earlier. We're not going to put all the resetting logic in here though. We'll put that into another method, which is a private void called newLevel. Void here means you just don't return a value. This is because we'll want to call this resetting code whenever we start a new level, such as after we're dead. This will get more complicated as we progress, but at the moment we've only got some basic bits in here. We set the game state to GameState.ready so the character can move, and then we make sure the character position is reset. We reset both our logical position in CharacterPos, which is our vector2 int, setting it to -1 like we currently have in the scene. Then we reset the actual position of the object. This is a vector3, and it's y equals 0.2 to put it on the grass, and z equals -1 again to put it before the level. Okay, that's our initialization sorted. Let's move on to getting the player input in the update method. I'm in Unity 6.2, which means what we have available by default is the new input system. This is great in that it creates an event-based system that provides greater flexibility and power. But for a short prototype like this, it's a bit overkill. You've got to set up a lot just to get input from the arrow keys. So we're going to use the new input system, but use it in polling mode in update just like the old one, rather than triggering events off the key presses. Most people are also probably more familiar with that, so I think that's the best trade-off. So, first up, everything here is going to be within an if statement. We're only going to take player input if our game state is in the GameState.ready state. This will stop us moving when we're dead, or already mid-move. We're going to start with a vector2 int move direction at 0. We're going to set this based on which key we press, and then we'll be able to use it to determine where we're going to move to using our CharacterPos. We've got a big if-else chain here for the movement. We only want to move one direction at a time. We're not allowing you to hold up and right and move diagonally. The first if will detect if the up arrow was pressed. In Unity's new input system, this is done with keyboard.current.uparrowKey. We don't want it to fire every frame, only when it's pressed. So we use the was pressed this frame. Simple. When we press any direction, 2 things are going to happen. First, we'll rotate our character so it's facing that direction. Up is the default way our reindeer starts, so we'll set the character.local rotation to quaternion.identity, so put it back to what it starts at, essentially. Then we'll set move direction's y value to 1 as we're moving up. Else, if it was the down arrow, then we rotate the reindeer to face backwards. We set the character's local rotation with quaternion.euler, so we can specify this in degrees. And we're rotating about the y-axis, which is pointing upwards, so that will be 180 degrees. And the move direction .y will be -1. Then the left arrow key, that's -90 degrees, and x equals -1. And finally the right arrow key, that's 90 degrees, and x equals 1. Okay, so after we've gone through that, we actually want to move. But we only do this if we've set the move direction, else we're just trying to move 0, and that's a bit wasteful. So if move direction is not equal to, that's what the exclamation mark equals means, vector2 int.0, then we want to move. But hold up, we can't just move anywhere, we've got trees and game boundaries and stuff. For now, we only have the start area, so we'll create a new method to let us know that's where we are. So a new private bool called inStartArea, which takes a vector2 int location. What this will do is return true if we're in the starting area and false if not. There are no obstacles in the starting area, so this is simply, is it in the area we've created? Our 4 open grassy areas were at y equals -1, -2, -3, and -4. We can check for that with if location.y is greater than -5, and the Boolean logic uses a double ampersand to do this, location.y is less than 0. You can do greater than or equal to -4 and less than or equal to -1 if you prefer, it all means the same. Okay, that's our forwards and backwards, but we have trees off to either side too. So we'll extend this to ensure that location.x is greater than -6 and location.x is less than 6. Remember, it was 11 wide, so the valid spaces go to plus or -5. If our target location satisfies that, we're in our big grassy area and we can just return true. Else, we're somewhere else and we don't know how to move there, so return false. Okay, now we've got that, we can use it in our update method. If in start area, and we want to know if our destination is there, so we pass that in, then we're good to move. So we update our character pos to set it to the new location, that's where we are now. And we'll start a coroutine called move character to animate the movement over to there. We'll create that right now. The move character method is of type IEnumerator. This is what we use for coroutines. An enumerator is something that loops over a collection of items. In our case in Unity, we often use that to iterate over our positions each update. The first thing we want to do here is set the game state to moving. This will block us from doing any other input until the character has finished moving. We also create a float elapsed time, which we set at 0 to track how far through the move we are. At the moment, we're in the starting area, but the height of the ground will change if we're on a road, so we'll need to get that. Add a new y height, which we'll hard code now to 0.2, as that's the height of our grass. We're going to interpolate between our start pos, which is just our current character position, and the end pos, which we create as a new vector 3 using our grid coordinates, in character pos for the x and z components, with our y height as our target height. Note that the vector2int in character pos has components x and y as it's 2D, but we're putting them into x and z in your vector 3. Now we've got that, we're going to use a standard coroutine lerp pattern you've probably seen before. While our elapsed time is less than the move duration, we're going to calculate the new position. Firstly, we calculate the percent we are through by taking the elapsed time divided by the move duration. That'll give us a number between 0 and 1. Then we update the character position, create a new vector3 new pos, which will use vector3.lerp to go between the start pos and the end pos based on the percent. Lerp just stands for linear interpolation. If percent is 0.2, then it'll return a point that is 20% between the start and end pos. Now we have the location we should be this frame, we set the character.position equals new pos. We record how much time has elapsed by adding on time.deltaTime to our elapsed time variable. Then we can go again. We use yield return null to say that we want this to run straight away next time and we don't want to wait. So this will give us the smoothest animation. Once the while loop has finished, you're not guaranteed to have executed that loop when percent equals 1. So we set the character.pos equal npos to guarantee we're there. The final thing to do is set the game state back to ready so we can move again. However, there is one thing to note here, is during gameplay we could have died whilst moving. If we've moved to the dead state, we don't want to go back to ready. So we'll just add a guarding if statement at the top to check if we're still in the moving state before setting it to ready if that's true. To our game manager script, we just need to add on the reference to our character object. Now, if we switch the game view, you can see that the camera is in a bit of a rubbish position at the moment. So let's just navigate the scene. I'm using Alt and left mouse button to rotate, middle to pan, and mouse wheel to zoom. That's a good area where we can see everything. If you right click on the camera, you can then click Align with View. Now we can check this out. You can see that when we press the arrow keys, our character is moving about. Not very gracefully, but it works. If you try and go out of the area into the trees or off the side, it doesn't let you. You'll probably note at this point that you have to keep pressing the arrow keys. That's because we used was press this frame. If you want to just be able to hold down the keys, then you can update the code to use is pressed. Because we have the guard on GameState.ready, it'll not fire until the last movement is finished. Let's make the movement a bit better, having the reindeer jump rather than slide around. There are two components of the jumping mechanism. The first is that we want the character to move upwards, the jump, but also we want them to face the direction they're travelling. To do the jump, we want a nice arc. There's many mathematical functions you could use to do this. I always recommend graphing them outside of Unity so you can see what's going on. Here's what I've chosen. This is done using desmos.com. It's half sine pi x for x between 0 and 1. The half at the front is just setting how high I want this jump to go, and the pi means we get back to 0 at 1 rather than pi. It's nice that it goes between 0 and 1, as we've already got that with our percent in our existing lerp. So in our code, we just need to update one bit in the move character method. When we are updating the character position in new pos, we can manually set the y value. This will be y height, because we need the offset from the ground, plus our function 0.5 times mathf.sine, mathf.pi times percent. You'll see that these math functions are in the mathf package, as you would expect. Back in Unity, we can quickly check this out. You can see we have a nice jump animation. All we need now is to make sure the character isn't so upright. In the code, we'll need an extra reference to do the rotation. Rather than rotating the whole character game object, we just want to rotate the model. This is because we don't want to rotate our collider. We just want that to remain firmly inside the character space, else we may end up with some collisions we don't want. Remember, we're not going for perfectly accurate collisions, but collisions that make the game feel right to play. So we add a new serialized field private transform for the character model. Then down in our move character method, at the top, we need to record what our start rotation is, putting the character model.local rotation into the start rotation quaternion. We'll just use this at the end to make sure we're back where we started. In our while loop, we can update the model rotation. First, take a vector3 rotation, which will set to the current character model.local rotation.euler angles. We want this because we only want to change the rotation in the x for the jump. Then we can set the character model.local rotation to be a new quaternion using the Euler method, so we can specify it in degrees. The function I'm using here is -5 times pi times cos of pi times percent. To get the actual tangent to the path, you differentiate our jump function. This is a slightly adapted version to make it less extreme. The character will rotate between about -16 and 16 degrees. In the Y and Z rotations, we just set them to the current rotation. At the end, we add character model.local rotation equals start rotation to ensure we end up back where we started. Okay, back in Unity. The first thing we need to do is drag on our character model into the game manager, then hit play. Now when our character jumps, it's a little less rigid. I think it looks better. If we set the duration to 2, it'll be much slower and we can see it better. You can tweak this function to make it smoother or change the dynamics entirely. I'll let you play with that. That's it for this episode. In the next, we'll implement the procedural generation of the grass and road tiles. I hope you found this tutorial useful in some way. As ever, the full code is on GitHub and linked in the description below. See you next time.